Hi to everybody who is attending today. I'm very glad to be being the expert on this webinar on e-waste plastics. I hope you can see both my slides and me somewhere. And if not, I hope Elisabeth will tell me. My name is Michael Gasser. I work for EMPA, and EMPA is a Swiss research institution who is doing a lot of work on electronic waste and plastic recycling in particular in developing and emerging nations. And I'll be happy to share with you today a bit my experiences, my views, and then happy to help you answer some of your questions that you might have. So these are the questions I've been informed that I should be covering today. I've tried to rearrange them a bit and classify them a bit. So we'll be discussing about technologies. How can I implement simple techniques to separate plastics? What sort of low-tech solutions are there? Then we're going to talk about some practical challenges people have experienced when opening up plastic recycling plants and or want to send e-waste plastics for recycling. So we're mostly going to look at shipment, and we're going to look at the disposal of plastics that can't be sold. And then the last part is going to be more about developing a market for recycled plastics. So to give you a bit of an idea what sort of players are there, what sort of customers you could be looking to or talking to, and what sort of plastics you could recycle locally. Now, I'm not an expert of all the countries you are from, so I'm just going to have to make do with a few examples of things we have done, and hopefully in the discussions then we can try and see whether these examples fit to your case. For those of you who have listened to me before, you know I tend to do quite a long introduction on plastics themselves as a material. As a researcher and as a recycler, it's important to know, but I just realized that we don't really have the time to go through it all in detail. That's why I've put it all together, or tried to put all the facts on plastics you really need to know to follow this webinar on this one slide. In the presentation that I will share with you, there will be more slides. So if you are looking for more detailed information, you will find that there. So e-waste contains about 20, maybe also 25% by weight plastic. And this plastic is made out of various types. You find the most common ones are called ABS, HIPS, PP, PC. Now, it's not really important to understand what these abbreviations stand for, but it's important to know that they're all different and they're all incompatible with each other to a large degree. So separating them is really key. So all these plastics I've listed up there, and in fact, almost all of the plastics in e-waste are what we call thermoplastics. That means they melt if you heat them up. So that also means that they can be recycled by melting them and reshaping them into new forms. One of the key exceptions here is the printed circuit boards, which are an epoxy resin, and they will not melt if you heat them up. So even though all of these plastics can be recycled in theory, not all of them are allowed to be recycled. So in a lot of plastics, especially from e-waste, you find hazardous substances that were used in the past because they gave some specific properties to the material. For example, bromidine to flame retardants, which kind of keep the distribution of flame on the lower side, or even help the plastic extinguish itself when it catches fire. Also heavy metals for various purposes. And nowadays, it has been realized that these substances are hazardous, and that also means that if you find or if you experience or have plastics that you want to recycle, you need to get rid of all the pieces that contain these hazardous parts before you can send them for recycling, because otherwise it can't become a product anymore. Now, there's a whole lot of details involved in that legislation, which we won't have time to cover in specific in the presentation, but if you have questions afterwards, I'm happy to answer it to the extent I'm able to. And of course, all these fractions that are containing hazardous materials, you need to not only separate, but you also need to dispose them controllably. And especially the brominated flame retardants are quite tricky in that regard, because even in the incineration, they can produce other hazardous substances that end up being even worse. So as I've already mentioned, sorting is really a key thing when we talk about plastic recycling or achieving a marketable plastic quality, and that has to do with the additives, with the hazardous additives. It has to do with processing characteristics, like how well a material will flow, and also the material properties. Think, for example, of the surface of a product made out of recycled material. If the plastic was dirty, then your surface will not be nice. There's also questions with regards, for example, to rigidity and so on that need to be considered. And if you mix all these different ABS, HIPS, plastics, and so on, you end up getting something that is not really, does not really have the property to be used in high quality applications. So I mentioned sorting being the key, and there's really two worlds in that whole sorting debate. One part is trying to sort the plastic that you might get out of e-waste on a piece basis. So let's say you dismantle a device and you get a whole housing, and then of course it makes sense that if you're able to say what sort of plastic it is, to sort the housings on this level. And there is flake-based sorting. That means you have first reduced the plastic pieces to smaller sizes, make them uniform, using something like a shredder where you make smaller pieces. You also maybe liberate pieces that do not belong. Maybe there's a screw in some of the plastic still left or something else that needs to be removed. And these flake-based sorting systems are way more technology-based. So they use physical properties of the material to separate and often employ machines, whereas the piece-based sorting is more kind of a manual thing to do. When we talk further down the chain in recycling, we need mixers in some cases where we add in, for example, additional additives. Let's think of a black color to make a nice and even color. You want to mix this in nicely with your flakes so that it's evenly distributed. And then at the end, something that is called an extruder, which is basically the piece of equipment that will melt your plastic through this screw and heat applied from the outside, and then produce either a product, as you can see here, or usually in a first step, pellets, which have all the different plastic flakes, which come from different housings, combined together and mixed together really well. And these pellets are basically what you would get out of an extruder, long strings of plastics being cooled down and then chopped into pieces. So there may be pinky finger-sized pieces or even smaller, a few millimeters. So all the technologies at the bottom that I've mentioned, shredders, mixers, extruders, sometimes you also talk about washing equipment, are things that are quite common. And you find them also in traditional manufacturing plants with using plastics. So there's not really too much to be taught about those technologies here in this webinar. And I want to focus way more on the top, which are things that are very specific to the recycling sector, A, and B, even when we talk about sorting according to different types or taking into consideration different additives, Um, you even want to look exactly at the stream you are selecting and the type of devices you are collecting, for example. And often, especially the machinery, you can see here some handheld devices as an example, or also some large-scale sorting systems tend to be quite expensive. So often it makes sense to try and replace these sorting devices as much as possible. And that's where very simple sorting methods come into play. And I'm actually going to talk about a few of those here. I've also arranged for a little bit of a show we can do, but I'm not going to do that during the presentation. Maybe if there is an interest afterwards in the discussion, we can do that, and I can really show these things to you. So there's various things you can use to help you identify both the type of plastic that might be contained in a piece or in a housing, as well as whether it contains brominated flame retardants or not, or other hazardous materials. And one of them is the origin. Where does it come from? So cables are something that tends to be produced from a completely different set of plastics that e-waste housings, for example. So if you are able to obtain cable plastics in a clean stream, it is much easier then to separate and identify the different plastic types. In flat panel screens, you, for example, find often a PMMA, or also called plexiglass layer, which is a transparent, very high value plastic that can be sold quite well. You also have, for example, from CRTs, it is very well known that which type of plastics you find there, and especially also that they often contain brominated flame retardants. So if you are dismantling and selecting which plastics you want to send for recycling, CRTs are not a stream to focus on. You should rather focus on trying to find appropriate disposal solutions for this material. Sometimes even specific manufacturers have very specific ways of employing certain plastics. For example, manufacturer A might only be using one type of plastic to produce keyboards. So if you know that, why bother spending time sorting these keyboards if you just know it's going to be the same. And that is a lot of knowledge that cannot be found somewhere in the literature, but is something that can be learned just by doing and trying out. Then there are the markings, which probably most of you are familiar with. Often we find abbreviations, like I mentioned in the beginning, PC, ABS, PS, on the inside of a housing, for example. There might be some additional remarks on it, like FR52, which denotes a type of flame retardant. And these are sometimes useful and sometimes not, because what often happens is the manufacturer will have produced a mold that people should use to produce a housing. And in that mold, it's already written what sort of plastic should be used. But often maybe a manufacturer of this housing will just procure another type of plastic. And then it will be what is written on the marking and what is true will not be the same. There are physical features like, for example, the flexibility and breakability. So there are some plastics which are more rigid, which tend to break very quickly when you try to when you apply pressure, and there are others which get very soft, and that will also help you to determine. There's a sound aspect to it, so hitting pieces of plastics will tell you something about what it is made of if you have trained your ears accordingly. Density, so different types of plastics have a different density. So using water or water combined with salt, you can actually differentiate between different plastics and sort them. As you can see in this example, there is the reaction to solvents, which just will help you to identify a certain set or even a single type of plastic. So there's some solvents which basically are very specific. So if you use this and have a reaction on the plastic, you know exactly what type of plastic you're dealing with. And there's also something that we see used a lot, but we can't recommend at all, and that is the smell of plastics when you burn a little piece of it. Of course, that is a hazardous activity, but it's something you see done in a lot of places, and actually also in the manufacturing industry. So when we talk about devices, just to give you a very short overview, there's mechanical sorting, which are on a flake basis, operate on a flake basis. They are able to sometimes to separate the plastics by type, by color, by additive content. And the way this works basically is that you have cameras which record each individual piece and then use different types of the spectrum, maybe X-ray or infrared, to determine what sort of flake it is. And these are very costly machines, but they are an option if you have a very high throughput of material. There are handheld devices, so devices you can use most often on a piece-based or on a housing-based sorting scheme, where different types of these devices help you to identify different things. So there is, for example, XRF units which determine whether there are hazardous substances in a plastic housing. There are NIR, so near infrared detectors, which help you to determine which type of plastic you're talking about. But they tend to be fairly costly for the benefit that you get. There's also some new of these handheld devices coming up, which are laser-based, and I believe some recyclers have made good experiences with those. But of course, acquiring such a device is only the beginning of being able to use it. You need to have people who are trained, people who know how to operate them. Some of those devices tend to break quite often, so it might be difficult to get repairs done, and so on. So let's go back to the two methods I want to go a bit into detail, and one is density. What I'm showing you here is a diagram, and on the left-hand side you can see different types of plastics. You might already recognize some of the abbreviations that I've already mentioned several times. And on the bottom scale, you see the density. And at 1.00, you see a line, and that is the density of fresh water. And the bars that you see is the density range of the different plastic types that are mentioned on the left-hand side. So thinking or using now the freshwater line, the 1.00 line as an example, you see that some bars are on the left side and some bars are on the right side of that line. And the bars that are on the left-hand side are HDPE and PP, two plastics you most often find also in household articles. And if the bar is left of these density lines, then you will know this will be a plastic that has a lower density. That means it will float in this water. There's another line you see at 1.08, and you see another line, the green one, at 1.20. And these are densities you can achieve by using fresh water and adding salts. And you see at the bottom, you see the quantities that you need to add more or less per liter to get that density. Now you can imagine, of course, depending on the amount of salt you add, you get a different density, which helps you to separate different types of plastics. And you get these sort of windows where you know that if I do several separations at different densities, I will only have a select few plastics remaining that all show the same behavior. What is really interesting, and what I won't have time to cover in more detail, but just to be mentioned here, you see that it's not just plastic types that you can separate. You also see the entry of BFR plastics, which is the fourth plastic type mentioned from the top. And you see these are comparatively very heavy, and BFR plastics usually are ABS and PS plastics, which have these brominated flame retardants added into it. So you see, if you do a separation at 1.08 or 1.10, you will be able not only to separate different types of plastics, but you'll also be able to separate brominated flame retardant plastic, which has to be disposed, from clean plastic that you can sell. The other thing I want to quickly cover in a bit more detail are solvents. And one of the solvents I would like to mention to you is acetone, which you can probably all buy somewhere in a shop as a nail polish remover. And this is a fairly broad chemical that attacks a wide set of plastics. It makes ABS, PS, HIPS, so a lot of the very common e-waste plastics sticky. And some of the plastics, if you use it, you have a white mark on it at the end. And then there is limonene, which smells a bit like orange, and is actually common in the orange peel itself. And this is a very specific chemical that only attacks PS and HIPS. So thinking about this now, you're able to combine these two in both detecting, okay, this is using acetone, okay, this is this group of plastics, and then using limonene to say, okay, and these are now the PS or HIPS parts. So that will help you already a lot in obtaining a clean fraction. And for those of you who are interested, this is we call that a sorting tree that we have developed to separate the most common e-waste plastics that you can find. And you start at the top with something we call a cut test that just helps you to decide whether a plastic actually melts when you heat it up, or whether it will be powdery, chippy, and will not melt when you heat it up. And then you do various tests with first these two solvents, so the limonene test, the acetone test, and then you follow up with various density tests, so either in the fresh water or in the salt water, that will then help you at the end to, for example, identify a HIPS, so a clean PS fraction that is free of brominated flame retardant, for example, from a HIPS fraction that contains brominated flame retardants and thus needs to be disposed, whereas the other part can be sent for recycling. Now I'm trying to get rid of this annotation again. I don't know how I do that. Now it should work. Okay, so that's it about sorting, recycling technologies. And I want to try now to cover really quickly a few of the other pitfalls that people can experience when trying to go for plastic recycling. One is certainly shipping, where you have a volume and a cost issue. Plastic waste, especially whole housings, they have a very low density, which translates to very high shipping costs. So the challenge is to sort of keep shipping costs low enough that you're still able to render a profit. And there's two ways to do that. Either you go into the direction of partially or completely processing the plastic, which might be possible or not. So that means you already shred your material to flakes, or you even go all the way to pellets. And that's why you're able to reduce the volume and thus make shipping more economically or less costly. You can also just try and cut the pieces by hand. That's also something that is practiced in some cases. Or you can go the route of baling. So that is, you have a specific machine that will produce bales, so press the plastics together and thus make shipping easier. Now, of course, if you go the baling route, you will not be able to generate a lot of value from your plastics, because all the value-added activities will be done by somebody else. The sorting, the shredding, the pelletization, and so on. And there is the other part, another issue people experience, and that has to do with compliance and regulation. So, for example, we've seen now in the last years China banning the import of plastic waste in many cases. Other countries are starting to follow suit, and often it's very difficult to get waste plastics to processors who are used to processing this material. There is also an issue in terms of interpreting import and export requirements, getting the right OKs in place from the authorities. It can take a very long time. And there's really no simple solution to that issue. But something I've seen being done quite often already is that material is processed to pellets, and that's why they somehow are not considered waste anymore, and then that then makes shipment way easier. Now, of course, if you want to go this route, you have to consider that once you have made a pellet, that is, you have mixed the plastic, melted it, you can't separate the different types out anymore. So you already need to have quite a bit of sorting infrastructure in place, so that you can produce pellets, maybe not in an industrial grade that can be sold, but at least in a way that it can be transported. And then whoever will be receiving the material from you will do the final touches, basically, matching the color, making sure it has a consistent quality, and so on. And another really tricky issue is the disposal of plastics that you can't recycle. And I've called it sort of the practical waste hierarchy. And I'm looking here at both hazardous plastics that I've mentioned before. They are non-compliant, they cannot be used in a product, they contain brominated flame retardants, heavy metals, or other plasticizers that have been banned nowadays. And I'm looking into non-hazardous plastics. So often, because e-waste contains so many types of plastics, you are left with small quantities of plastic of a certain type you can't sell. So also those you need to dispose to some extent. And I've tried to order a bit the things that can be done locally to dispose them from better to worse. But before I start mentioning these options, I just want to say this is a very rough estimation. It really depends on what you have locally available, of what the local rules are, and also the priorities are of something like an environmental protection agency in where you or how you would dispose these materials. For hazardous plastics, the best thing to do, and actually one of the only really best applicable technology, is what I would call, in a very simple way, special incineration. So that is an incineration in a high temperature with a specific air scrubbers and a guaranteed destruction of these of the hazardous substances, or a removal into a specific waste fraction coming out of the incineration. Then, as the next best possible step, and this is also probably the best step for non-hazardous plastics which cannot be sold, is to use them in an incineration process which uses or recovers energy. So that might both be an industry process, let's say a smelter, or it might also be a specific waste incinerator that is coupled with energy recovery. For non-hazardous plastics, you just need to have general emission control in place. For hazardous plastics, it's important to dilute this material down to a small percentage of the total input feed, so you don't get spikes in your hazardous substances in the incineration process. As the next best option, and we're getting more and more towards worse, is a controlled landfill. That means a landfill that has liners in place. For hazardous plastics, you would be mostly looking to even establish a separate compartment. So that means if at some point people notice that hazardous substances leak out of these plastics, they can be dug out again and then possibly destroyed, go in a final destruction. If that is not available, a normal landfill is an option. And if that is not an option, you can still look into something like a non-target recycling. So for non-hazardous plastic, we're just talking about plastics which do not have to conform to a lot of quality requirements. So something that is very common is to, for example, make very thick fence posts, create wood plastic composites, so a mixture of maybe sawdust and plastic for producing panels, outdoor benches, everything that just needs a lot of material but doesn't need to be very nice and shiny. And for the hazardous plastics, you can look, at least in some cases, to use the recycling exemption of the Stockholm Convention. So the Stockholm Convention is what regulates the disposal, the production of these hazardous substances that you find in plastics, especially brominated flame retardants. And the Stockholm Convention contains an article that says you can still recycle this material under specific circumstances. And it's a quite exhaustive list. And at the end, it boils down to having a complete control of the second life cycle. So let's say you recycle housings which contain hazardous substances into a new product. You need to both ensure that during the production there is no release of the hazardous substance, during the use phase there is no release of the hazardous substance, and during the disposal of this product you have produced, you're able to collect this and dispose it completely at that point in time. And then, of course, really at the bottom, there is an uncontrolled burning, maybe just in a small scale, or really as a kind of a smoldering, smoldering burn that just produces a lot of smoke. Now let's look at a bit the brighter side of plastics recycling, and that is to look a bit at markets and applications for these materials. And I've tried to structure a bit what can be done with plastics of a, let's say, high quality. You have I would say the common applications, which are more big scale, big mass, but low margin. So you're looking into producing consumer products or components of consumer products. You might be looking to go back into electronic and electrical equipment. You might be looking into other engineering applications, for example, automotive market. You might be looking into household applications. And then there is the other side, which is a bit small scale but more high margin. So there are people who have started to do waste art using plastics. There are a lot of emerging industries, for example, the 3D printing industries, which needs filaments, which on a per ton basis are very, very costly. And I imagine a lot of emerging and developing countries will have communities, 3D printing enthusiasts who who might be very interested in using cheaper material for figuring out how to use 3D printing. And then, of course, for all these applications, depending, of course, a bit on the domestic market, you have customers internationally and in some cases domestic. And I just wanted here to list a few examples that I find are very well documented in terms of kind of, I would say, international examples. There's a very nice example of 3D printing filament being produced by Coolrec and Refill, and I believe there's also somebody here from Coolrec today. So if there's questions, maybe this representative is willing to give some answers afterwards. There's the website Perpetual Plastic Project, which gives quite some interesting ideas of what to do with waste plastic in terms of art. There's a nice documentation by Philips of what sort of components they in small household appliances they use recycled plastics for. There's an example of stamps being produced from e-waste plastic, and you'll see all these links when you get the presentation. But what I really want to focus on now is to talk more about domestic use, domestic applications, and of course that really depends on the country. Depends on what sort of manufacturing you have in your country. And also depends on what sort of plastic products are demanded locally. So depending on the country, you might have very specific things being used. And each of these manufacturers that already exist or importers that import certain products will be importing material or products made from a specific plastic type. So you can't be using all of these plastics for all the applications. And that needs a bit of research to figure out, well, where could my plastic or one of the plastics I produce as an e-waste plastic or e-waste plastic recycler be used? And maybe we can discuss that a bit later. I just want to go through a few examples that we've been working on in the last years. So one of the things that are often a challenge is that not just the recycling process itself for e-waste, but also that the e-waste plastic is in the informal sector, and the informal sector has already its own channels, its own applications, and might not be producing material of a sufficient quality to really go into a high quality application. And we worked together with Plastics for Change, a NGO in India, to try and find a way how to do that. And they were more established in the part of obtaining the material, whereas we helped them develop a process that would actually lead to a product that can be marketed towards the producers of components for electronic equipment. And here you see more or less the general flow chart, the processes that were used. So starting from this mixed material, we did some manual segregation. And what is important here to know is that not only did we have to identify what type of plastic it was, so here we were looking for ABS, but also we had to make sure that we're not introducing heavy metals in a too high quantity. So cadmium is an element that has been banned nowadays or restricted in use for the electronic sector. So we were not able to, based on these analysis, use red and orange ABS plastic as an input feed for our process. And that's a simple reason, or the reason why is because cadmium used to be used as a pigment and sometimes still is for this red, yellow, orange type of colors. So we had to make sure we remove those. And then after a size reduction, a chipping step, we would be going into these density cuts, and we actually have three density cuts to at the end then obtain a pure ABS fraction you see at the bottom here in the flow chart. And after that you go into pelletization, doing the lab tests and really doing the product production. And this is something that has been running as a pilot, and now we will be looking to scaling it up. But it seems to be working the way we have implemented and the way I've shown it to you here. Another example is to go more a bit into other engineering applications. For example, car bumpers might be an interesting thing to do. We worked together with a recycler in India that tried to do closed loop recycling of car bumpers. So that means a broken car bumper is reprocessed into a new car bumper. But I'm also aware that in some parts of Western Africa, e-waste plastic is procured to produce car bumpers. And that, of course, then is not in the brand quality, but that's an aftermarket quality, but might still be an interesting downstream option for e-waste plastics. And this is something more of a household product example, and here starting off with mixed cable plastics from Ghana that we saw. So somebody was operating a cable stripping machine, was able to recover or sell the metals. He was able to get out of this, and the plastic was just sort of left, and nobody knew what to do with it. And when you know a bit what sort of plastics you have, you can come up with a very simple separation step, getting out the PE as one of the main components of cable plastic and the PVC. And we were able to find for both plastics manufacturers of products within Ghana who could then replace some of the virgin material with that waste plastic. What was really interesting here, and I think that might be something that applies to a lot of other countries as well, is that the import of virgin plastics was very highly taxed in Ghana when we did this project. So that made it very cost effective for a producer of buckets or wastewater pipes to use recycled plastics. So here there was really an interest in cost reduction that drove this whole experiment. And just as also a careful or a side note, especially PVC can again contain a lot of different hazardous materials. So you need to really make sure if you use this for recycling that you are legally compliant with all the relevant laws. If there's really no solution for your material locally, and this was also a case here from Ghana, I'd like to show you. These were plastics that came from cooling appliances, so mostly fridges. And there's of course the foam, which is very tricky to manage, and there's not really a recycling solution available for that in most cases. But there's also a lot of the rigid panels and the boxes inside of the fridge and so on that could theoretically be recycled and would be of a very high value because it's white or clear plastic. But in Ghana, the issue was that there's actually nobody using these types of plastics. So the only thing that was possible to do is to sort this mixed heap of plastic into different types and then send it for export. So you see here, this is also sorting by color to some extent. One way to make a bit more money out of the sale of housings. So these have been a few of the examples. I hope I didn't talk for too long. Thank you for your attention, for listening. You find here my email address, so I'm very happy to receive feedback from you, questions from you, even after the webinar. You also find this link, sustainablerecycling.org. This is the project website of a project I've been working on, where we actually developed all these examples that I've shown you now. So you'll find more resources there as well. And yeah, with that, I'd like to end my presentation and give the word back to Elisabeth, or maybe to anybody who has questions.